Okay, so we're going to build two basic tools for counting, and we'll use those to knock down, these 5 problems, which I'll quickly go through, and you can see if you can solve them before we get to them. We'll knock them down one by one. Okay, so menus. So my choices for breakfast are pancake, waffle, Doritos. Lunch, my choices are burger, Doritos. And dinner, my choices are salad, steak, Doritos. So I like Doritos. If you're ever wondering what to get me, Doritos. Okay, so, in a day, I pick one breakfast, one lunch, and one dinner. How many different daily menus can I construct? Okay. New York plates have the format capital A, B, C, so you can figure out what that is. 1, 2, 3, 4. Okay. How many registered vehicles are possible in New York State? Okay. Think of a race with 10 student runners. Okay, and you look at who came first, second, and third. So how many top 3 finishers are possible? And, how many race outcomes are possible? So what if you looked at the entire race outcome, who came first, second, third, all the way up to 10th? Okay, how many race outcomes are possible? Okay, now let's move a little bit closer to home. Password. So, you've started, you've got your newfangled account on YouTube or Google or whatever, and they ask you to create a password. And the typical characters are, the lowercase letters, 26 of them, the uppercase letters, 26 of them, the digits, 10 digits, and there are these special characters, exclamation point, blah, blah, blah. There are 10 special characters. Okay, so here's a typical example of the rules. Okay, for creating a password. It must be length 8. Now, sometimes they say length 8 or longer, but just to simplify, let's say it has to be length 8. And you need at least one special character. These days, that annoying thing, put at least one special character. So your password has to have one of these weirdos in there. Okay, so how many valid passwords are possible? Okay. Now, why do we care? I'm just going to pick one of these passwords. Why we care about the number of valid passwords is if someone is trying to hack into your system, they'll have to try every password until one succeeds. And so how long will it take? If they're going to try every password, in the worst case, it can take the number of passwords times how long it takes to test one password. Okay, so this allows us to figure out how long a hacker can take to break into your account in the worst case. Okay, and one final problem. So you have your 10 students again, but now they're forming a party planning committee. So a party planning committee can consist of any subset of the students, okay, including the empty subset. So how many possible party planning committees are there? Okay, how many party planning committees? We'll knock these down one by one, but before we do so, let's develop these 2 very basic tools. Okay, so we'll start with the 3-bit binary sequences. So 3-bit binary sequences. Okay, and I'll informally write that as the sequence B1, B2, B3. Okay, and how many of them are there? Okay, so we can list them out. In this case, we can list them out. There's 000, 001, 010, 011, 100, 101, 110, 111. Okay, and the number of these is equal to 8. Okay, so for this particular example, we can list it out, but let's do it more systematically so that we can generalize. Okay, so if we write the binary sequences as the 3-bit binary sequences as B1, B2, B3, so you have B1, B2, B3. There are 2 cases. The last bit can either be 0 or it can be 1. Okay, so this sequence is either of the form B1, B2, and a 0, or B1, B2, and a 1. So we can consider these as type 1, and these as type 2. Okay, and suppose there are n1 of these and n2 of these. Okay, then what we're saying is that every 3-bit binary sequence is either of type 1 or of type 2, and it cannot be both. And so if there are n of these, then, it doesn't take much to convince us that the total number of 3-bit binary sequences, n, is equal to n1 plus n2. Okay. The number of binary sequences that end in 0 plus the number that end in 1. And that's our first, most basic rule. We call it the sum rule. Okay, so the sum rule. If you have n objects and n1 of type 1 and n2 of type 2, then n equals n1 plus n2. Okay? Now, it's important that every one of your objects must be type 1 or type 2, cannot be both. So every one of your objects is either type 1 or it's type 2. Okay? And so So sometimes we say that these types are disjoint, they don't intersect. Okay? They're mutually exclusive types. Now, if we put this in sort of a set notation, think of a set A, which has my n objects, okay? And think of a set A with my n objects, and what we're saying is that A is the union of two sets A1 and A2, the type 1 objects and the type 2 objects, and they're mutually exclusive, so A1 intersection A2 is the empty set, and what we're really saying here is that the size of A, the number of objects in this disjoint union, is equal to the number of objects in A1 plus the number of objects in A2. Okay? And clearly this sum rule, okay, it's a very basic rule. It says if you're counting something up, there are two types, count up the type 1, count up the type 2, and add. And clearly this generalizes to more than two types. If there are 3 types, same thing. 4 types, same thing. K types, same thing. Okay? So let's box it. This is the sum rule. Okay, so the number of sequences, B1, B2, B3 is equal to the number of sequences B1, B2 followed by 0 plus the number of sequences B1, B2 followed by 1. So the number of sequences ending in 0 plus the number of sequences ending in 1. But these are just 2-bit sequences ending in 0. So the number of these is exactly the number of 2-bit sequences. It's exactly the number of 2-bit sequences, and then you just add a 0, plus the number of 2-bit sequences, and then you just add a 1. Okay? So this is twice the number of 2-bit sequences. Okay, so we applied the sum rule, and we find that the number of 3-bit sequences is twice the number of 2-bit sequences. We can continue this argument again. So the number of 2-bit sequences, so this guy here is going to be twice the number of 1-bit sequences. Because again, there are two types of 2-bit sequences. B1 followed by 0, B1 followed by 1. Okay. And so this equals twice times 2 times the number of 1-bit sequences. And this is the number of 1-bit sequences. That's easy. That's just 2. So this is 2 times 2 times 2. And we have gotten 8 as we did before, okay, in a more systematic manner. Okay. And this way of getting the number 8 for 3-bit sequences easily generalizes to n-bit sequences, and we won't be able to list the n-bit sequences like we did for 3 bits, okay? But we can compute the number of n-bit sequences. So let's immediately generalize. Okay, the number of n-bit binary sequences. So n-bit binary sequences, B1, B2, B3 up to Bn. Okay, is just going to be, same argument, but we have to iterate that argument n times. So that's number of B1, B2 up to Bn binary sequences is just 2 times 2 times 2 times 2. Okay, and there are n of these. Okay, so this is 2 to the n. Okay, nice. For example, 10-bit binary sequences equals 2 to the 10 equals 1024. I particularly highlight this because, as a computer scientist, you should know the powers of 2. 2 to the 10 is 1024, and it's a useful approximation to realize that this is approximately 1,000. So 20-bit is 2 to the 20, but now that's much harder to remember exactly. But since we know that 2 to the 10 is 1,000, 2 to the 20 is 1,000 squared, so this is approximately 1,000,000. Equals 1,000 squared. Okay, some useful manipulations with powers of 2. Okay, now let's develop our second rule. Okay, and it's really a generalization of this, way in which we counted the binary sequences, which is we took the product of 2, n times. Okay, and so the next rule we're going to develop is called the product rule. Okay, product. Now you can actually derive the product rule using induction and the sum rule. So really there's only one rule, the sum rule, but it's useful to have the product rule. So let me give you an example. So, Malik's getting ready, for class, and he has 6 shirts. He has 6 shirts, white, blue, purple, orange, green, yellow. So he has 6 shirts. I don't know. You'll never see me wear that yellow shirt. You'll only see me wear the orange shirt when Orange Malik comes up. Okay, so Malik has 6 shirts. Okay. And for each shirt, okay, Malik has 4 possible ties that will match, let us say. Okay, so if he chooses the white shirt, he has 4 choices for ties. If he chooses the blue shirt, he has 4 choices for ties, and so on. Okay, so how many outfits does Malik have, and are there enough outfits to, so that he can wear a different outfit for every one of the 28 lectures? Well, we see it. He has 4 plus 4 plus 4 plus 4 plus 4 plus 4. That's just 6 times 4 outfits. 6 times 4 outfits. Okay, now the interesting thing here is that Malik picks a shirt, okay, in one of 6 ways, and then, having fixed his shirt to one of these, he has one of 4 ways to pick the tie, and so the number of outfits is 6 times 4. So let's generalize that as a product rule. Okay, so let's say you're doing something and it involves steps. Okay, step 1, step 2, step 3, up to step K, and each step has a particular number of ways of being performed. For example, this step has 6 ways, picking the shirt. And then after you pick the shirt, you have 4 ways of picking the tie. Okay, so you have K steps. Okay, and we will sort of represent what you do in each of your K steps by the sequence X1, X2, X3, up to Xk. Think of X1 as what shirt did you pick? So X1 would be, so in this case there's X1, X2, and X1, let's say if I pick so what shirt did you pick? So X1 would be one of these, WBPOGY, and X2 would be the color of the tie. Okay. So in general, there are K things you have to do, so you have to specify K things in some particular order, and let us say that there are X1 there are N1 ways to choose X1. So there are 6 ways to choose my shirt. Okay. Now, after you choose X1, so after I choose my shirt, after fixing X1, okay, so after fixing X1, there are N2 ways of choosing X2. So after you pick your shirt, there are 4 ways to choose your tie. After fixing X1, there are N2 ways to choose X2. Okay, so after X1, there are N2 ways to choose X2. And then after X1, X2, so after you've picked your shirt and tie, now there are 6 ways to pick your pants. Okay, so there are N3 ways to choose X3, and so on. And and in the last step, you've picked the K-1 guys. So after X1, X2, up to Xk-1, there are Nk ways to choose Xk. So you tell me all the various choices you made in each of the number of ways possible. And now I'd like to know how many possible ways are there of, determining this sequence, or in this case, determining the shirt and the tie. How many possible ways? Okay, and the product rule says that the total number of ways, N, is just the product. N1 times N2 times N3 times N4 times all the way up to N5. Nk. Okay, so that is a very simple product rule. Okay, and this is an example of the product rule. Okay, so the binary strings of length n. Okay, you have to, so x1, x2 up to xk is just b1, b2 up to bn. So this has 2 ways of being chosen. This has 2 ways of being chosen, and so on, 2 ways of being chosen. The product rule says multiply all those together, and you get 2 to the n. So this rule is a special case of the product rule. Okay, so now let's knock down our problems, and they're going to be easy now with these 2 basic rules. Okay, so problem 1, menus. Okay, so you, just like the shirt and the ties and so on, you need to tell me breakfast, lunch, and dinner. So you need to tell me breakfast, lunch, and dinner. Okay, and there are 3 ways to choose breakfast, 2 ways to choose lunch, and 3 ways to choose dinner. So the product rule says multiply. So the number of possible daily menus is the product of these 2 equals 18. So if I wanted to, I would fill in this thing here with 18 possible daily menus that are all different. So if you got that number before we got there, well done. Okay. let's knock off the New York plates. 2. New York plates. And New York plates. Okay, now we have to interpret this, license plate format. Well, it suggests that, the first 3 characters are uppercase letters, and then the next 4 characters are digits. Okay, and we'll assume that the uppercase letters, there are 26, and the digits 0, 1 up to 9, there are 10 digits. Okay, so we have A, B, C, 1, 2, 3, 4. Okay, so there are 26 ways to choose an uppercase letter. 26, 26, 10, 10, 10, 10. So the product rule says multiply all these things together. And so you get 10 to the 4 times 26 cubed, which is approximately 176 million. No problem. New York State has a population of 20 million, and not everyone has a car. Okay, so we have more than enough license plates to register the vehicles that we will need in the near-term future. Okay, so no problem. Let's knock off another one of these. If you got something like this, wow, well done. Okay, racers. Okay, so how many top 3 finishes? Well, I have to tell you who came first, who came second, and who came third. Let's call it F, S, and T. Okay, and there are 10 children, there are 10 runners, so there are 10 choices for this. There are who came second, there are 10 choices for this, and there are 10 choices for who came third. So 10 times 10 times 10, oh, that's 1,000. So 1,000 possible top 3 finishers. Okay, except that this is wrong. That's wrong. Okay, now here's a problem. Yeah, not that it's a problem. This is where you have to be careful. So it is indeed true that all the 10 students can come in second. So there are 10 possibilities for who came in second. But we have to go back to the product rule and read it carefully. What it says is that suppose there are n1 ways to choose x1. Okay, after you choose x1, there are n2 ways to choose x2. And the key is that after you choose x1, so it's kind of after I've chosen my shirt, how many possible ties are there? After you've chosen who came in first, okay, there are no longer 10 people who can come in second. Because we're assuming, in a reasonable, normal world, that the same person cannot come both first and second. Okay, so after you've chosen first, there are only 9 people who can come in second. Okay, and after you have chosen x1, x2, after you have chosen first and second, there are only 8 people who can come in third. Okay, and now we get the right answer for the number of top 10, top 3 finishes. So this is 10 times 9 times 8. Now we can apply the product rule, and we get 720. Okay, so let's fill in some of the answers. How many registered cars possible? Approximately 176 million. Okay, how many top 10 finishes? 720. Okay, how many race outcomes? When you look at all the people running, so 10 ways to decide who came first, 9 ways to decide who came second, 8 for third, 7, 6, 5, 4, and there's 1 way to decide who came last. Now, that doesn't mean that that there's only 1 way to determine who came in last. There's just only 1 way to determine who came in last after you have determined all the other guys. So after you have determined, first to 9th, that leaves just 1 person who came in 10th. So for all the races, it's 10 times 9 times 8. So for all the runners, all runners is 10 times 9 times 8 times 7 times times 2 times 1. This is 10 factorial. Okay, so the answer here would be 10 factorial. And if you got 10 factorial, fantastic. Wow, you're way ahead of me. Boom. Okay, let's go for the password. That's a very interesting, tricky one. Okay, and it's also very current and very, close to home for computer scientists. Okay, because we're all paranoid and we don't want anyone hacking into our system. But it's not an easy one. So let's start. Now that's a little bit tricky. Let's start with, so the rules are that the password has length 8 and it has to have at least 1 special character. Okay, so there's going to be a little bit of subtle reasoning here. So let's forget about this at least 1 special character and just let's compute the number of passwords of all possible passwords. So, all possible passwords, okay, is a string of length 8. So you have to tell me, 8 characters. Character 1, character 2, character 3, up to character 8. Okay. So if you didn't care about this 1 special character that annoys the heck out of everyone. Okay. Well, there are 26 here. So how many choices for character 1? There are 26, lowercase letters, 26, so that's 26 plus 26, 52, plus 10 digits plus 10 special. So that's 72. Okay, so there are 72 choices for character 1. Okay, and there's no difference for character 2, character 3, or character. This is not like the races. You can repeat your password could be A 8 times if you want it. Okay, so there's 72 for each of these. So the number of passwords in total is the product, which is, so the total number of passwords is 72 raised to the power 8. It's a big number. Okay. Now, I'm going to use the sum rule in the following way. I'm going to say that the number of passwords is equal to the number of passwords that have a special character or more equals passwords with special plus passwords without special. Okay, password with special plus password without special. Okay, and okay, so this we know, this is equal to 72 to the power 8. Okay, so how many passwords are there with special? That's what we're trying to compute. How many valid passwords? Okay, and how many passwords without a special? Well, if you're not allowed to use a special character, then the number of characters you can use in each spot is not 72. It's 72 minus these 10 special, so this would be 62. So the number of passwords without a special is 62 raised to the power 8. Same exact counting argument, the same exact product rule, but with 62 characters instead of 72 characters. You can choose 8 characters, and each character can be one of 62. Product rule, 62 raised to the power 8. And in this indirect way, using the sum rule and the product rule, we can compute the password with a special. So the password with special, okay, so valid passwords is equal to 72 raised to the power 8 minus 62 raised to the power 8. This is approximately equal to 5 times 10 to the 14. Wow! Passwords, how many valid passwords? 5 times 10 to the 14. So we'll put the answer here. Approximately equal to 5 times 10 to the 14. So technically it's 72 to the 8 minus 62 to the 8. Now that was a challenging one. If you got that, you're ready to teach this class. Okay. All right. It's an interesting, so nowadays the websites have gotten more sophisticated, and they're not only requiring at least one special, but they're requiring at least one special and also at least one uppercase. Okay. Now, interesting challenge. Can you figure out how many valid passwords are if you're not only required to have at least one special, but also at least one uppercase? That's a little more challenging. Okay, so you can work your wheels on that one. Okay. Now, if a hacker could test one password, let's say, in a millisecond, then this would take roughly 6 months. So 6 months to hack into your account, to hack in on 32K core, on a 32K core machine, on 32K cores. So now you can work this out. I'm not going to go through the details. So roughly speaking, it'll 1 millisecond to test one password, okay, to see if it'll work. If it fails, they try another. In the worst case, they have to, it's 10 to the 14. In the worst case, they try, approximately 5 times 10 to the 14 password, 1 millisecond for each. That's 6 months on 32,000 cores. Okay. So they could, in principle, get in. They could hack into your account in 6 months. And that's why you will always find in most of these systems that they prompt you to change your password every 6 months. And then if you don't, it just blocks all access because it's going to assume that you've been hacked. Okay. All right. Let's do the last one, which is the student committees. We actually saw something like this when we discussed discrete objects and sets. Okay. Which is basically we're asking for how many objects, how many subsets are there in the power set of a set of 10 students. Okay. But let's use our basic counting rules to solve that problem. Okay, so problem number 5. So you have 10 students. Okay. Now I'm going to show you an interesting way of deciding who's in the committee. Okay. So you have 10 students, S1, S2, S3, S4, up to S10. Okay. And an interesting way of deciding who's in the committee is to just go one by one, through the students. Just like when I'm getting ready, I go one by one through the things I need to do. I need to wear a shirt, then a tie, then a pants, then a belt, then a socks, then a shoes, and so on, right? So let's go one by one through each student and say yes or no, they are in the committee. So I'll use a 1 for yes and a 0 for no. So 1 or 0, are they in the committee? 1 means yes. Okay. 1 or 0, are they in the committee? And 1 means yes. And so we keep doing this and until we get to the 10th student, 1 or 0, are they in the committee or not? And by the time we're done with all the 10 students, we have now some of the students are in the committee, those to whom we assign 1, and the other students to whom we assign 0 are not in the committee. So now we see a relationship that picking a student committee corresponds exactly to picking a binary sequence of 1s and 0s, where the 1s will tell you which student is in the committee. So for example, if my sequence was 1, 1, 0, 0, 0, 0, 0, 1, 0, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this says that I've picked S1, I've picked S2, and I've picked S8. And that's my committee. Okay? And this is an interesting sort of correspondence. We call this a one-to-one correspondence. So every student committee can be sort of realized by specifying a unique binary sequence. So once you want, a 10-bit binary sequence, and once you tell me the 10-bit binary sequence, you tell me what the committee is, and if you tell me the committee, I can figure out what the binary sequence is. So there's this correspondence between 10-bit binary sequences and a student committee. So the number of student committees must exactly equal the number of 10-bit binary sequences. Or, using the product rule, you have 2 times 2 times 2 times 2 times 2 up to 10. So the number of student committees is 2 to the 10, which is equal to the number of 10-bit binary sequences. Okay. And there. So 2 to the 10, which is equal to 1024, and I'll just emphasize again, this is approximately 1,000. So commit to your memory banks that 2 to the 10 is approximately 1,000. Okay. This relationship between committees and binary sequences will come back, and we'll use that same relationship a little bit later. So that relationship between committees and binary sequences is important. So make sure you understand it. Okay. Let me give you a couple of interesting counting problems that, have relevance to hard problems that we like to solve in computer science, and then we will move on. Okay. So